Today, we're going to follow the incredible journey of metal, all the way from a humble rock in the ground to a solid railway track. It's a fantastic story of chemistry, a ton of energy, and some serious human ingenuity.
I mean, think about it for a second. Every single piece of metal you use, the stuff in your phone, your car, pretty much everything, it all starts out as just rock. But how in the world do we get from that to this? Well, let's break down exactly how it's done.
So here's our game plan. First up, we've got to find the right kind of rock. Then we get to the really cool part, what I'm calling the great separation. After that, we'll give it a final polish to get it ready for use. And to wrap things up, we'll look at the constant battle against rust.
Okay, so our quest begins deep inside the Earth's crust. But here's the thing, you can't just grab any old rock and hope to find metal. You have to know exactly what you're looking for. You've got to be selective. And that brings us to a really, really important distinction. You see, a mineral is basically any chemical compound that occurs naturally. But an ore, well, an ore is special. It's a mineral that has enough of a metal we want to make it actually worth all the cost and effort to extract it. So think of it this way. All ores are minerals, but not all minerals are good enough to be called ores. And what you're seeing here is that metals aren't just sitting around in their pure form. Nope. They're chemically locked up with other elements, like oxygen or sulfur, inside these compounds. Our whole job is to figure out how to pick that lock and set the metal free. All right, now for the main event, the extraction. This is where the real magic of chemistry happens, where we use some clever techniques to break those chemical bonds and finally free the pure metal. Now, you can't just use the same method for every metal. There's no one-size-fits-all solution here. It all comes down to how reactive the metal is. You see, the more reactive a metal is, the stronger its compounds are, and the more energy we have to throw at it to break it free. It's like a chemical battle, and your strategy has to match your opponent's strength. So we can pretty much sort all metals into three main groups based on that reactivity. At the very top, you've got the super reactive metals like sodium and aluminum. Then in the middle, you have the ones with medium reactivity like iron and lead. And way down at the bottom are the least reactive metals like gold and silver, which are so unreactive you can sometimes find them just lying around in their pure form. And this slide really lays out the different strategies we have to use. For those highly reactive metals, the chemical bonds are just too strong for simple heat. So we have to hit them with a powerful force, electricity, in a process called electrolysis. But for the less reactive metals, we can usually just persuade them out with heat in a chemical reaction called reduction. Okay, let's make this super real. Picture this. You need to join two gigantic steel railway tracks together right out in the middle of nowhere. You can't exactly bring a giant extension cord and plug in a welder, right? Well, the solution is just an absolutely spectacular piece of chemistry in action. It's called the thermite reaction. And what you do is mix iron oxide, which is basically just fancy rust, with aluminum powder. Now, because aluminum is way more reactive than iron, it aggressively wants that oxygen. So it literally rips the oxygen atoms right off of the iron oxide. The result is pure molten iron and an incredible, unbelievable amount of heat. We're talking temperatures over 2,000 degrees Celsius. This liquid metal then flows right into the gap between the rails and solidifies, creating a perfect, strong, seamless weld. It's basically a portable furnace and a welder all rolled into one. Just amazing. So, we've extracted the metal, but our job isn't quite done. What we have is called crude metal, and it's still full of impurities. For high-tech stuff, it's just not clean enough, so it needs one final polish. A fantastic example of this is how we refine copper. What we do is we take a big, thick slab of our impure copper and a thin, clean sheet of pure copper, and we stick them in a special chemical solution. Then we pass an electric current through it. And what happens is, copper atoms literally leave the impure block, travel through the solution, and plate themselves onto the pure sheet, one atom at a time. All the junk, all the impurities just fall to the bottom. What you're left with is 99.9% pure copper. And trust me, that purity is absolutely critical for things like electrical wires. Even the tiniest impurity can mess up the flow of electricity and cause big problems. All right, on to our final section. We've gone through all this incredible effort to take a rock, break it apart, and purify the metal inside. But here's the catch.
The entire time, nature is constantly trying to undo all of our hard work. It's a process we all know as corrosion, or simply rust. We see rust all over the place. But have you ever stopped to think about what it actually takes for it to form? Well, a super simple experiment can show us exactly what's needed. So, just imagine 3 test tubes, each with a regular iron nail inside. In the first one, tube A, the nail is sitting in some water, exposed to the air. For tube B, we boil the water first to get all the air out, and then we put a layer of oil on top to seal it. And in tube C, we put in a chemical that sucks up all the moisture, so the nail is just sitting in completely dry air. Now, you let this sit for a few days, and when you come back, the result is crystal clear. The only nail that has any rust on it is the one in test tube A, the one that had both air and water. The big takeaway here is undeniable. You need both. It's not one or the other. For iron to rust, it needs to be exposed to both oxygen from the air and water. If you take away either one of those, corrosion stops in its tracks. And that, right there, is why painting metal or coating it works so well. It's just a barrier to keep both air and water out. So that leaves us with this one final, kind of profound thought. All of metallurgy, this entire massive global industry, is really just a constant fight against nature. We have to pour enormous amounts of energy into forcing metals into their pure, refined, but unstable state. And the second we stop protecting them, nature begins its slow, relentless process of pulling them right back to their more stable, original form, turning our shiny cars and strong railway tracks, bit by bit, back into simple rock.